22.6 Motion of a charged particle in a uniform electric. In this session, we will outline the key topics covered regarding the behavior of charges in uniform electric fields. We begin with the fundamentals of particle motion in these fields. Next, we will discuss how to determine the acceleration of these particles and review the relevant analysis models. To make these concepts concrete, we will examine two specific case studies. The first case study looks at the acceleration of a positive charge moving parallel to the field lines. The second case study explores the motion of an electron moving perpendicular to the electric field. Finally, we will conclude with a brief comparison between these electric field models and the gravitational models you are already familiar with. Let us get started with the fundamental principles. Let us start by modeling a charged particle in an electric field. When a particle with a specific charge and mass is placed in an electric field, it experiences an electric force. The magnitude and direction of this force are equal to the charge times the electric field. If we assume this electric force is the only force acting on the particle, then it represents the net force, which causes the particle to accelerate. According to Newton's second law, or the particle under a net force model, the net force equals the mass of the particle times its acceleration. By setting the mass times acceleration equal to the charge times the electric field, we can solve for the resulting acceleration. This gives us an acceleration equal to the charge multiplied by the electric field, all divided by the mass of the particle. We now narrow our focus to uniform electric fields. If the electric field is uniform, meaning it has a constant magnitude and direction, then the electric force exerted on the particle will also be constant. Because the force is constant, the particle's motion can be described using three familiar analysis models. First, the particle is in a field. Second, it is a particle under a net force. Third, because the force is constant, it is a particle under constant acceleration. The direction of this acceleration depends on the sign of the charge. Positive charges will always accelerate in the exact same direction as the electric field. Conversely, negative charges will accelerate in the direction directly opposite to the electric field. Let us look at a case study involving an accelerating positive charge. Imagine a positive point charge that is released from rest at a starting point, which we will call point A, located next to a positively charged plate. Because the charge is positive, it accelerates toward the right, moving toward a negatively charged plate at point B, covering a total distance called wood E. Since the field is uniform, we can model this as a particle under constant acceleration. We use the kinematic equation, stating that the final velocity squared equals the initial velocity squared, plus 2 times the acceleration times the change in position. The initial velocity is 0. By substituting our previously derived expression for acceleration, we find that the final speed equals the square root of the quantity 2 times the charge times the electric field times the distance, all divided by the mass. We can solve that exact same problem using an alternative approach, specifically the energy analysis model. In this method, the charge is treated as a non-isolated system in terms of energy. As the particle moves, work is done on the charge by the electric force. This work translates directly into a change in the particle's kinetic energy. We can write this relationship as the electric force multiplied by the displacement equals the final kinetic energy, which is 1/2 times mass times final velocity squared, minus the initial kinetic energy of 0. By substituting the electric force with the product of charge and electric field, and replacing the displacement with the distance d, we can algebraically solve for the final velocity. The final speed again equals the square root of the quantity 2 times charge times electric field times distance, all divided by the mass. As expected, both the kinematic and the work energy approaches yield absolutely identical results. Now let us examine a different scenario, featuring an accelerated electron. Suppose an electron enters a region with a uniform electric field, but this time its initial velocity is perfectly perpendicular to the electric field lines. Because the electron carries a negative charge, the electric force acting on it points in the opposite direction of the field. In our diagram, the electric field points straight up, so the force on the electron is directed downward. This downward force creates a downward acceleration. Because the electron maintains a constant horizontal velocity while simultaneously accelerating downward, its resulting trajectory is a curved, parabolic path. This behavior is mathematically identical to the projectile motion of an object thrown horizontally in a uniform gravitational field. Let us perform a quantitative analysis of this parabolic motion. First, the vertical acceleration is determined by the electron's charge and mass, yielding a negative value equal to the elementary charge times the electric field, divided by the electron mass. For the horizontal motion, there is no force, so it is modeled as moving with a constant velocity. The total time the electron spends between the plates simply equals the horizontal length of the plates divided by the initial horizontal velocity. For the vertical position, we use the constant acceleration model. The final vertical position equals the initial vertical position plus the initial vertical velocity times time plus 1/2 times the vertical acceleration times the time squared. Also, it is important to note that gravitational forces are entirely neglected in these calculations. For tiny atomic particles like electrons, the electric force is trillions of times stronger than the gravitational force. To summarize our discussion, when charged particles are placed in a uniform electric field, they experience a constant acceleration. This acceleration is directly proportional to the charge and the electric field, and inversely proportional to the particle's mass. When the particle's motion is entirely parallel to the electric field lines, you can easily analyze the situation using either constant acceleration kinematics or the work-energy theorem. On the other hand, if a particle enters the field with a velocity perpendicular to the field lines, the constant perpendicular force results in a parabolic trajectory, which is completely analogous to two-dimensional projectile motion. Finally, always remember that for subatomic particles, the electric force is so immense compared to gravity that the gravitational force can be safely ignored. Before we conclude this module, please take a moment to consider a couple of review questions to test your understanding. First, think about why the motion of an electron projected perpendicularly into a uniform electric field follows a parabolic path rather than a circular one. What specific features of the forces at play cause this shape? Second, ask yourself under what specific physical conditions it becomes mathematically valid to apply the particle under constant acceleration model to a charged particle moving through an electric field. Reflecting on these questions will help solidify the core concepts of particle kinematics and electric forces we just covered.